Thank you for having me. Hello everyone. My name is Sanji and I'm a PhD student in the Space Plasma and Climate group at Imperial. So that's in the Department of Physics. And today I'm going to be talking to you about Earth observation and how I specifically am using Earth observation and all of that kind of stuff. So the first question I think we should kind of answer is what Earth observation actually is. So, I mean, it's pretty much what it says on the tin. It's just a way of observing the Earth from outer space. Now, what's really useful for is monitoring our planet. And with things like climate change and things like deforestation, it's really useful to have and use. Now, what's particularly good about it, at least in my opinion, is that using the things we observe from space, the actual physical evidence of things changing, we can provide that as proof for policy changes to show that we need this mitigation for this thing or this mitigation for this thing. So it's a really good way to justify that. And then following on from that, we can actually use these satellite images to track the progress of that policy and see if it's actually working and actually having the effects we want it to. Now, I'm just going to give you a couple of examples of how we can use Earth observation and how people in the National Centre for Earth Observation do use it. So the first example is in this satellite image here. So I don't know if you remember, but earlier this year and at the end of the last year, there were massive wildfires in Canada. They were a lot more severe than they were expected to be, and they produced a huge amount of smoke. And this is a satellite image of some of that smoke kind of tracking across North America. And there was so much, and it was just like it was a huge thing moving in the atmosphere that even reached parts of Europe. And so this is just a satellite image of that. And so using Earth observation, we were able to monitor it and also kind of expect where it was going. So to see the effects on things like air quality in different places. Now, another example is looking at volcanic eruptions. So this is a pretty cool one. This is the Hunga eruption that took place in 2022. And this volcano is an underwater volcano. I can't remember how far underwater, but it was underwater. And so when it erupted, it put a huge amount of water vapor into the atmosphere. It got as high as the stratosphere. And I'm not sure if you can really see it in this photo, but in other photos, you can see the top of its plume kind of plateauing as it hit the pressure level. Now, this is a really cool event in itself and an interesting thing to study. But what we can do with this is improve our understanding of different chemical reactions in our atmosphere. And that's just a really useful thing to be able to do. Another example that's very different is tracking the melting of different things. So what you can see here is the melting of a glacier. So this photo, this collection of photos is from a European Space Agency's Earth observation satellite. You can see how the glacier is kind of melting away. And that same concept can be applied to things like the breaking of Arctic shelves or sea ice breaking up and those kinds of things. And so that's a really good way to track the effects of temperature changes in the poles. And then finally, a very different example is looking at deforestation. So here you can see 4 different panels that are the satellite images of the same region. And you can see it starting in 2013 and ending in 2018. And what you can basically see is how trees have been chopped down in this region. The area has been burned and then it's been repurposed for a new pasture to, I don't know, have like calves and animals and grow food and things like that. And so this one in particular kind of relates to that tracking the process of policy changes and seeing maybe if areas are being cut down that shouldn't be, or how much is being cut down, how much needs to be cut down for things like growing food. Now, the way that I use Earth observation is a little different. And as you might have been alluded earlier, it's all to do with the greenhouse effect. So I'm just going to run through what the greenhouse effect is and kind of bring it down from a big picture to a small picture of what I'm doing. So the first thing you should know about the greenhouse effect is it's a good thing. It's how our planet's habitable and it's what keeps us warm. And the way it starts with is sunlight coming from the sun. Now, in that sunlight, you have little packets of energy. And sunlight is just a form of radiation. That's all radiation is. And so as the sunlight comes from the sun, that radiation hits the Earth and warms the Earth. Now, when something gets hot, it emits radiation of its own. And if it was just a rock or something like that, if that got hot, it would emit the radiation and cool down. But what's special about our planet, and is common among a lot of other planets, is that we have an atmosphere. Now, some radiation can still escape from this atmosphere, but a lot of the radiation is trapped and kind of scattered and absorbed and sent back down to our planet, warming it again. And then because it gets hot, it emits radiation. And this cycle kind of continues and is what keeps the Earth warm. And it's a really good thing. It's a really powerful effect. The problem is that human activities are increasing the amounts of greenhouse gases. And so more radiation is being trapped and the Earth is getting hotter, and then it's emitting more radiation, and then you have that kind of cycling effect. Now, when I say greenhouse gases, I mean things like carbon dioxide, methane, but also water vapor, things that are trapping and keeping the radiation in. Now, when we talk about the greenhouse effect and look at the greenhouse effect in detail, it's important to consider the different energies and wavelengths that are associated with the process. So on the left-hand side here, you can see a little schematic thing of the electromagnetic spectrum. So all of the energies associated with radiation. And on the far left, you've got the higher energy stuff with the shorter wavelengths. So things like gamma rays, X-rays, UV light. And then on the right-hand side, you've got the lower energy, longer wavelength stuff. So things like infrared, the microwaves, and radio waves. And I've also zoomed in on the section surrounding visible light, which is kind of the middle. And you've got UV, visible, and infrared there. Now, when we go back to the greenhouse effect, what you've got coming from the sun, as you'd expect, is the higher energy stuff. And when we're talking about the kind of stuff I do, we're talking about UV and visible light coming from the sun. Now, when that radiation hits the Earth and warms it, a little bit of energy is kind of lost in that process. And so what comes out of the Earth is infrared radiation. And infrared radiation is just thermal radiation. It's basically the same thing. So when we talk about the infrared coming out of the Earth, it's useful to split up into different sections just to kind of make it easier to look at. And so I've got the near, mid, and far infrared. So the near infrared is the shorter energy, shorter wavelength, higher energy stuff. And the far infrared is the longer wavelength, lower energy stuff. And then you've got mid in the middle. Now, when I'm talking about the far infrared, rather than talking up to 1 millimeter in wavelength, I'm only talking up to 0.1 millimeter, which is the same as 100 microns. And I'll be using microns throughout the thing. So microns are just kind of 10 to the -6 of a meter. So currently, we know we've got this near, mid, and far infrared radiation coming out. And when we look at the kind of bulk amounts of radiation coming out at each specified set of wavelengths, we know how much there is. And it actually turns out that, or at least models suggest, over half of the radiation reaching the top of the atmosphere is within the far infrared, and that's a really huge amount. Now, knowing how spectrums work, if you go from, they don't really have a resolution of 1 micron, for example, they're not little blocks, they're kind of a continuous flow of numbers. And so when we translate that to a plot like this, we get a curve. This isn't necessarily the correct curve that you see, but it's just an example. And in the near and mid infrared, we've measured this curve. We know kind of the detail that's associated with it to a pretty high resolution. But when we look in the far infrared, all we have is that bar plot. We know how much there is as kind of a fixed value for this fixed range. We don't really know the detail. But that's due to change with the number of space missions launched in the next couple of years, one of which launched last week, or the week before maybe, and has taken the first measurements of the far infrared at high resolution. Now, my work is focused on the European Space Agency's Explorer mission. So this is their 9th Earth Explorer mission, which is a set of kind of Earth observation missions, and it's due to launch in 2027. And it will be measuring the outgoing long wave radiation in the far and mid infrared. Now, it'll be doing so to hopefully quite a high resolution, and it'll be doing it across the globe. So we'll get that kind of information across the entire planet. So what would Vorum actually see when it's launched? That's the first question I'm going to pose to you. Now, here is an example of a satellite image. Now, this is from a completely different satellite called MODIS, and it's taken over the north of Australia. So you can see there's a little bit of coast, the green bit, and you've got a little bit of desert, and then you've got the ocean or water above it. And then you can also see there's things like there's clouds kind of in a way, different types of clouds with a lot of different kind of looking vibes about them. And then you can also see that there's clear spots where there's no cloud. And we call that clear sky, which is just no cloud. Now, when Forum gets an image like this, each individual pixel that you see here in the satellite image will relate to a measurement of the outgoing radiation. And so what we can do with this is relate the different things you see in the image to the actual measured spectrum, the measurements of the radiation that's coming out. Now, let's relate it back to the greenhouse effect, because that's what I'm actually interested in. So there are 2 steps I'm going to break the greenhouse effect down into. We're going to ignore the sun for a second. So the first thing is the actual radiation emitted by Earth. so how it's emitting its radiation. And it turns out the amount it's emitting is actually dependent on the actual different surfaces, so if it's land or sea, for example. And the second thing is the actual radiation that's trapped by the atmosphere. And that's the different gases, or maybe even clouds, that are absorbing and scattering the radiation. And so that's the second aspect we're going to talk about today. So let's go back to the surface and see how forum observations will help us understand the Earth's surface better. So here, just in this example, you've got three different surface types. You've got sea or oceans, you've got land. So land can come in a lot of different varieties. You can have forests on your land, you can have deserts on your land, you can just have grass. So there's lots of different variation. And then you can also have ice or snow, or ice or snow. So what you find typically in the poles, in the Arctic and Antarctica. Now, each of these has different properties. And because of their different properties, they have what we call different emissivities. And the amount of radiation emitted, if they're all heated to the same temperature, varies depending on their emissivity. If they have a lower emissivity, then less radiation is emitted. If they have a higher emissivity, then more radiation is emitted, if they're all heated to the same temperature. So if we go back to this example, let's start with the ocean. Ocean can typically have lower emissivities, and so it's emitting less radiation. And we move up to land, where it's slightly higher, and then we get slightly more. And we move up to something like snow, and it can be quite high. And so that's really important to consider when you're observing Earth and when you're measuring the amount of radiation coming out, because it won't be constant across the entire planet. Now, I'm just going to show you an example of what something like forum would measure if there was no atmosphere at all. So if we're just looking at the surface, we're just looking at this rock that's being constantly heated in different ways. So this is an example of a spectrum that I would see. Now on the top, we've got wavelength. So on the left-hand side, we've got 100 microns, which is the longer wavelength, lower energy stuff. On the right-hand side, we've got going down to 6 microns. And then on the bottom, I've inverted that to get wave number. Wave number is just typically a parameter that we operate in because it kind of represents the amount of energy. So you've got the lower energy stuff on the left and the higher energy stuff on the right. And you can see I've marked on the far infrared and the mid-infrared regions. Now, this is the far infrared region I'll be talking about. The mid-infrared does extend to lower wavelengths, but I'm just looking at this limited spectral region for now. And then on the y-axis, we've got the top of atmosphere radiance. And that is just a measure of the amount of radiation reaching the top of the atmosphere at each of these wavelengths. Now, there are 3 curves that I'm showing you here, each with different emissivities. The purple one has an emissivity of 1, and that's the highest emissivity you can get. It ranges between 0 and 1, and so that's showing the maximum amount of radiation that's reaching the top of the atmosphere. And then you go down from 0.8 down to 6, which is the lowest. And so just from looking at this graph, you can see how big an effect the emissivity of the surface has on the amount of radiation that's being emitted. And so let's kind of flip that around and imagine you're a satellite observing this measurement. Let's say you're observing the blue curve, which has an emissivity of 0.8, but you think the emissivity is 1. That's going to throw up the temperatures you're thinking about when you're looking at it. So the emissivity is something that's really important to nail down for different materials. Now, for the next step. Oh, I forgot to mention, emissivity actually varies with wavelengths. So what I've shown you here is that emissivity is fixed across wavelength, but it actually varies. And particularly in the far infrared, it's not super well understood because it's just a limited number of observations from the top of the atmosphere. And so it's a bit more of a problem than the other parts of the spectrum. So now let's move up a level. We've got different amounts of radiation coming out from our surfaces. Now let's take a look at what's in our atmosphere. So the first thing we're going to talk about are different gases in our atmosphere, the greenhouse gases that are trapping the radiation. So I mentioned water vapor, carbon dioxide, and I don't know if I mentioned methane, but that's another one. But I'm just going to be focusing on water vapor for most of what I'm talking about. So the way these work, I'll show you here. This is a water vapor molecule. Water vapor molecules can move. They can jiggle. They can move in all sorts of different ways. And it takes a certain amount of energy to get them to move in a certain amount of way. Now, it turns out that that radiation that's coming up from the surface that's hitting these molecules in the atmosphere is at the correct wavelength to make the molecule move like that. And so when that radiation hits the molecule and it moves, and then it emits its own radiation because it's moving, emits its own form of energy, that is what's causing the trapping effect that greenhouse gases do. And that's why greenhouse gases trap radiation, and the greenhouse effect is occurring when you're talking about gases. And so, yeah, so they send radiation in all directions and trap it down. Now, the next thing I'm going to talk about is clouds. So there are many different types of clouds, but I'm going to simplify it to two different types. The first is water clouds. So these just have a bunch of different spherical water droplets inside of them. And the second is ice clouds. Now, these are just ice crystals forming in air, forming big clumps. And when you look outside and you kind of try to translate these to the sky, the water cloud are the fluffier ones, the kind of lower ones. And ice clouds are a lot more wispy, and they form much higher up where it's colder. Now, you can get mixes of these. You can get, half ice, half water, more ice. And you can actually sometimes see the progression of one changing to the other, which is really cool. But I digress. But what these two can do is scatter the radiation. Now, they also absorb, but they can also scatter. So if you think about a beam of light hitting a glass of water and how that beam of light moves, that's basically what's happening here, but with different wavelengths. And so they kind of have the same effect and do the same thing. Now, I'm only just going to talk about the water vapor now. I just thought the clouds were a cool thing to add. So what you see now, this black curve, is what we call a spectrum that would actually be observed by Forum. Now, this is for a clear sky case, no clouds whatsoever. And in purple, I've put the curve that would be observed if there was no atmosphere. So you can see the effect of what the different gases are doing. And you can see there's a lot more spectral detail in different regions. So you've got water vapor absorbing and kind of trapping in the far infrared, dominating the far infrared. You've got carbon dioxide doing stuff between around 600 to 800 per centimeter. You've got ozone at around 1,000 per centimeter. So that big drop there. And you've also got water vapor plus a number of other gases absorbing kind of 1,100, 1,200 onwards. And so you can see the huge amount of, the huge impact they have on the observed spectra. Now, I want to talk about water vapor specifically for a moment. You can see that so if you imagine no atmosphere is the purple curve, if you add more water vapor, you move that black curve down. You kind of change the shape of it, and you change the aspects of it. And because water vapor is such a huge absorber in this region, this is one of the reasons it's such a big greenhouse gas, because so much radiation that's going up is in the far infrared, and water vapor is the main one absorbing in that region. So it's really important to understand. So that's kind of a summary of what Forum would see and what we're working with to start with. Now I just want to talk to you about how we're preparing for this actual space mission to go up, because obviously Forum hasn't launched. And so now everything we're doing at the moment is just prep for it. Now, I'm not an engineer. I also don't work at ESA, so I can't talk about the logistical stuff or the more mechanical things, but what I can talk to you is about how we're preparing for it in a scientific way. So the main reasons for starting it now is because these missions cost a lot of money. And so you want to start developing and testing the tools to actually apply to the observations before they launch, and you want them to work. So what we do is test them with simulations from different models to get them as good as they can be. The other thing is to actually consider it in the development of the satellite. Now, this is because Forum's due to launch in 2027, that's relatively soon, so a lot of that will have been done before. But it's to know things like if the far infrared is particularly important in a certain region. And I should also mention that I am part of one team of many different teams who do a lot of really amazing stuff to do with Forum. And so this is just a little piece of the massive puzzle that's going into it. So how am I actually helping to prepare for Forum? Well, that's to do with fieldwork. And to me, this is one of the major advantages that comes up with Earth observation. You get to do fieldwork on the actual planet that you're measuring, which I love. So let's go back. So this is the spectrum that Forum would measure. So this is what you'd see in one individual pixel of a Forum image. And I've mentioned very briefly that the emissivity of different materials and different surfaces isn't super well known in the far infrared. And one of the reasons for that is because water vapor is a huge absorber in this region. And so you can see that it's having a big effect on the spectrum. And so it won't be able to pick up the detail you see in the emissivity of different materials in that region. So the first thing that we did fieldwork-wise was to get a better understanding of the emissivity of different materials in the far infrared. And to do that, we need it to be dry. And so for it to be dry, we went to the Arctic Circle. So here you can see Almar Observatory. It's an observatory in an island just off the coast of Norway, that's still part of Norway, and it's just inside the Arctic Circle. And here you can see a photo I took on the ground of it. So you can see kind of vaguely the outline of a hill range and the observatory is on top of that hill where that green line is shooting out of. And that green line is not something I've added. That is a laser that's at the observatory that is shot up into the sky. It's used to measure the atmosphere. And in this case, it was being used to measure the aurora. And that has nothing to do with what I work on, but I just think that's really cool. So here's a photo of me on top of that hill right outside the observatory. And you can see I've got this instrument next to me. Now, this instrument is called Finesse. It's a really cool instrument, and it can kind of measure what form would be measuring. It's slightly different, but it's the same kind of principles. So that gray or silver box is shown here in this rough schematic. So what I'm going to talk to you about now is just how we're actually measuring the emissivity of the sample. So what we put in the box of very nicely labeled sample were different types of ice or different types of snow. So you can change the grain size of snow. And what we did was actually measure the temperature of the sample and then point Finesse at it to measure the emissivity. Now, the actual process to do so involved measuring a couple of other things and different levels of the radiation, but essentially what we were looking at was the emissivity of the sample like this. So if we translate this to what Forum would see, we just replace Finesse, the instrument, with a satellite, and it will be seeing a very similar thing. And in fact, it'll actually be seeing a very similar thing over the poles, you know, in the Arctic or Antarctica. And so this is one of the ways we can kind of prepare for a mission. So that's the surface stuff to do with the greenhouse effect. Now let's talk about the atmosphere. So I mentioned that we've got things like water vapor and different cloud types in our atmosphere interacting with the upwelling radiation. So what we want to do first, or what we can do first, is fly a plane through these to measure them. So for water vapor, what can be done, or what has been done, is we have a little measurement device on the plane, and we just drop it and release it through the atmosphere. And it measures things like the temperature profile and the water vapor profile. And then you also have instruments on board to measure other gases as well. Now, for the clouds, what you have are probes fitted on the plane to measure things like the particle sizes or the amount of water or the different shapes of the ice crystal particles. And so that's what it can do there. So using this method, we have a really good understanding of what our actual state is. And then what we do, we fly our plane. We fly our plane over the different things and fit something like Finesse on the plane to measure the upwelling radiation as it goes through it. So now what we have are actual measurements of the state and the spectra that will be observed, a spectra that's kind of like what Forum would see. And so this gives us a little head start. And this is what we can start testing our tools on and start kind of picking apart the science in preparation for the Forum mission. So now we've prepared for it. And now we're actually ready for the real thing. So now I'm going to show you what we're actually going to do with the data that's taken by Forum. So fundamentally, what this mission is all about, and what most Earth observation missions are all about, are understanding our atmosphere and improving our understanding of our planet. Now, the far infrared region in particular, it's very sensitive to water vapor and also the properties of ice clouds. Now, first I'm going to talk about water vapor. So water vapor is our strongest greenhouse gas. As I've mentioned, it's a huge absorber in the far infrared. And so we really want to know how much of it is in our atmosphere. Now, it's not something that's hugely affected by human activities, maybe not like CO2. It is kind of affected by other processes, but not as much as stuff like that. It's not something we're actively pumping into the atmosphere. But it's a huge player, and it's really important that we nail it down. And currently, we have uncertainties of up to 15% at higher altitudes, so kind of where aircraft fly. There's a larger uncertainty there. And so we really need to get that together and understand it. And Earth observation is a really neat way of covering a really huge space of our planet over a shorter time period than we would otherwise. So going back to that spectra, you can see I've blocked out the far infrared because we don't have those observations super well yet. All we've got is the mid-infrared. And water vapor in this region absorbs kind of between 1100 to 200 and a bit further on. Now, what we can do is infer the amounts of water vapor in our atmosphere from a spectrum like this that's been measured. So the purple line is, again, with no atmosphere. That's kind of the maximum radiation it could observe. And the black line shows the effects of the water vapor. Now, if you add more water vapor, the black line will go down and will move further away from the purple line. If you reduce the amount of water vapor, that black line can go up and meet the purple line. So what you can tell from this region is that that black line's not got a lot of freedom to move. And what this means is that the spectrum that are observed are less sensitive to the amounts of water vapor. So when we're trying to guess and work our way backwards, it's a bit harder to because there's less information. But if we move to the far infrared, you can see there's a huge amount of freedom for that black line to move up and down. It's got a lot of kind of freedom and flexibility to move. And so that gives us more information. A small change in radiance will give us a lot of information. And so in theory, including the far infrared and having measurements of the far infrared will improve our knowledge of the amount of water vapor in our atmosphere. Now, it's actually been shown by someone else in my group that this is true. So what she did was apply that kind of principle to the observations that were taken by an instrument on an aircraft. So here you can see two plots. So the y-axis shows the actual altitude, the x is the amount of water vapor, and the black line shows the measurement. So what was measured when that device was dropped out of the plane, measuring the profile. The dark blue shows the predicted, so what models suggested would be there. And in green on the left, you've got something that only uses the far infrared. In light blue, you've got something that only uses the mid-infrared, so looking at those specific spectral regions. And then on the right-hand side, you've got a combination of both. Now, what you can see, if you just look on the left-hand side plot, is that the far infrared seems to do a lot better job than the mid-infrared alone. Now, this could just be due to the specific instruments that were used, but if you look on the right-hand side, you can see combined, particularly between like 4 to 6 kilometers, that's the easiest place to compare. It does seem to do the best job when they're combined together. And the far infrared has really, really helped with it. And so what this shows is that the far infrared is very likely to improve our estimations of water vapor. Again, those observations is really going to help from forum. And what this will mean, better estimations of water vapor means better weather predictions, better approximations of the greenhouse effect, and so climate change, and also a better understanding of atmospheric dynamics. Now, going to the other thing, which is ice clouds. So ice clouds are a huge problem in climate models. They're super complex. They can form in a variety of different conditions based on different stuff. They're quite sensitive to things like the amount of water vapor, the actual temperature, and so they're quite hard to nail down. And one thing about them that's kind of I find interesting is all of the different shapes that the particles can form. So here you can see 9 different example shapes that ice crystals can have in ice clouds. And the far infrared has actually been shown to be particularly sensitive to the different shapes the ice particles, can form within the cloud. And so we can apply the same kind of principle that we use for water vapor to this. So what I'm going to show you now are 3 different combinations of ice crystal shapes. So in the first one, we have what we call a general habit mix, and this is just a bunch of different ice crystal shapes. It's not necessarily the ones that I've got here, but it's just a mixture of shapes. Then the second combination is just looking at one of those. So these are called solid columns. And you can see it's just been filled with different solid columns. And then the final mix is what we call aggregate solid columns. And that's where they've just been combined to make these bigger particles. And so using these 3 different combinations of different ice crystal shapes, I'm going to show you what form could observe. So on the top, you've got the actual spectra, and on the bottom, you've got the differences, but we'll look at the top first. So again, you've got 100 microns, actually less than 100 microns on the left-hand side, but longer wavelengths. And on the right-hand side, you've got shorter wavelengths. And on the bottom, that translates to the inverse in wave number. So again, left-hand side is the far infrared, right-hand side is the mid-infrared. And at first glance, this spectra on the top looks very different to the clear sky ones. And that's easy to explain if you imagine a satellite looking down on the planet. What you see when there's no cloud is you can see right down to the surface. But if there's a cloud in the way, even if it's a fairly thin one, it's kind of blocked out some aspects. And so that's why you see this more kind of smoothed out shape. You see a bit less detail in it. Now I've plotted on the top all 3 different combinations, but it's kind of hard to see. So I've shown the differences on the bottom. And you can see the differences between the first combination, the general mix, between combinations 2 and 3. And if we just look at the mid-infrared again, because we only have really good observations in the mid-infrared, you can see that when we compare the first combination and the second combination, there's quite a big difference between the two. Between the two. And when we look at the far infrared, we see an even bigger difference between them. And then again, if we look at combination 3 versus combination 1, you can see a bit of a smaller difference in the mid-infrared. And on the left, we can again see a bigger difference in the far infrared. And what this basically tells us is that the far infrared is sensitive to different shapes. And so when we're trying to retrieve information from the observed spectra, we'll be able to maybe do it better with stuff from Forum than with one that's only looked in the mid-infrared. Now, I want to bring it back to the bigger picture of what I was talking about. So Earth observation generally is just a powerful tool to monitor our planet. The outgoing long-wave radiation, so the thermal radiation that's reaching the top of the atmosphere, is being measured for the very first time in the far infrared this year, and with pre-fire, which is focused over the poles, and we've got another one going on in the next couple of years that will capture it globally, which is very, very exciting. The second thing is that outputs from both of these missions will be used to improve our understanding of our planet. So we can use it to understand our water vapor distributions better, and also understand the properties of ice clouds more and how they form and where all the different structures come from. And so this can be used to improve things like weather prediction. And this is the weather prediction for this week in London. So I'm sorry, everyone, because I thought it was going to be something this weekend. But then also things like the atmospheric dynamics, so different circulations patterns that you can see, and then also climate change. And climate change is obviously the big one that we're talking about here. Now, I just want to take a step back from talking about the greenhouse effect and the Forum, and just show you all of the different missions that are part of the Earth Explorer mission. So this is the European Space Agency program. And you can see there's like, I think 9, 10 missions, and I think maybe they're getting ready for the 11th as well. And you can see they're measuring things like the ice, the magnetic field, clouds and aerosols, photosynthesis. There's a huge variety of stuff being measured. And this is only from one Earth observation program that ESA has. And ESA is just one space agency in the world. And so there's so much you can do, and there's so much that's being done with Earth observation that's really quite exciting. So yeah, thanks for listening, and thanks for having me. And I hope you've gotten a little bit excited about Earth observation and maybe learn a little bit about greenhouse effects as well.